everyone. Welcome to RN tutorials on mechanics of fluids. And in this video lecture, I am going to explain about metacenter and metacentric height. Not only about metacenter and metacentric height, I'm going to explain you how to find out or how to derive an equation for metacentric height. So first, we try to look at the definitions of metacenter and metacentric height. Here, how can we define a metacenter? It is defined as a point with respect to which a body oscillates in a liquid when the body is tilted through a small angle. Okay, so when the body is submerged in a liquid and when you try to tilt it through a small angle and when you release it and whatever the oscillations are taking place to the body, and those oscillations may be taking place with respect to a particular point. So that point can be called as your metacenter. So we try to analyze some more little. So here I am taking one container into which I am inserting one body that is submerged into the liquid, and when you tilt this body, so assume this one is axis, and when you tilt the body, so this body can oscillate into this liquid with respect to a particular point. So oscillations are taking place means those oscillations take place only with respect to a particular point. So with what point, with respect to what point the body can oscillate inside the liquid, that point can be called as the metacenter. So we try to look at that point location also. So for that, in the same container, I'm taking the object, and when the body is submerged, and here I would like to represent first center of gravity position, which will be exactly in the middle of the height of the body as per our shape, that is a rectangle we have considered. And similarly, as we know the knowledge of center of buoyancy, the center of buoyancy also acts always below the center of gravity. So approximately I'm representing the center of buoyancy location below G, that is the center of gravity of your body, and at the same point B, the buoyancy force acts, which will be equal to the weight of the body which is present inside the liquid only, and try to extend it. And when we tilt that body, okay, so when you tilt the body here, what is happening? The center of gravity and the center of buoyancy is displacing its position, changing its position. And but even with you tilt the body, the actual center of buoyancy acts at the same point. It means it means the force of buoyancy acts at the same point only. So that is why it takes place at initial position only. I'm assuming is as B1, and this B becomes its changed position, but actually the force of buoyancy acts at the same position as it is taking place initially whenever you insert the body. That means before in tilting condition. Okay, that is the changed position B, and the line of action of the force of buoyancy acts at the same point B1. And here when you try to extend this line of action of the force of buoyancy, here it will be intersecting the neutral axis of body. This one is neutral axis line. So this extended line of action of the force is intersecting at a particular point to this neutral axis of the body. So that intersecting point only the metacenter with which the body is going to oscillate when you tilt through a particular angle. Okay, now so this point is only the metacenter of the particular body. So that means by this analysis again we can define the metacenter also in another way. It means how can we define? The definition can be given. It can be also defined as an intersecting point between neutral axis line of the body and the line of action of the force of buoyancy. Okay, it is an intersecting point between neutral axis of the body and line of action of force of buoyancy. So that is a metacenter. So in this way also we can define the metacenter. In two ways we can define. One is the point with which the body oscillates in a liquid when it is tilted, then that point can be called as a metacenter. And at the same time it is an intersecting point in between the neutral axis of the body and the line of action of force of buoyancy when it is tilted through a particular angle. So that is about metacenter. Next we go for metacentric height. How can we define a metacentric height? The metacentric height, it is a distance which is considered between the center of gravity of the body and metacenter of the body. So here it is defined as the distance between the metacenter and the center of gravity of the floating body or submerged body inside the liquid. That means as per our figure here, the metacentric height represents gm. The distance between g and m is the metacentric height here. Okay, that is about metacenter and metacentric height. So next we try to derive an equation for the metacentric height. So how can we derive an equation? So for that again I am considering one body which is immersed in a liquid, and initially I am locating the level of the water with respect to the body surface here. So this blue line represents the level of the water whenever the body is immersed in a liquid, but when you tilt it, the water level won't change, but the layer of the body which is aligning with this level line of the water will be changing its position. So that position I can represent with a black line over the body. So initially when it is not tilted, this black line can be aligning with the blue line which represents the aligning position of the body with the water level. But when you tilt it, the layer which is aligning with the water level will be changing. So that can be represented like this. And here, and except that everything is same, uh, that is center of buoyancy acts at the same point and the force of buoyancy also acts at the same point here. Okay, so here next we can say when you are tilting here, what is happening? The body, the some part of the body is getting inside into the liquid and some part of the body is going outside the liquid. So however you tilt, the weight of the body which is to be present inside the liquid won't be changing here. It will not be changing here, but its position is changing. That means here we can say in another way, the weight of the body on the right hand side of the neutral axis is increasing and the left hand side is decreasing. So here increasing, it is decreasing, so there will be no change in the weight of the body. At the same time there will be no change in the quantity of the force of buoyancy which is acting at the center of buoyancy. But one more analysis we can give. Here there is an increasing weight is taking place. Assume that weight as W. So when the right hand side weight is increasing, when you keep on increasing by increasing the tilting angle, the body completely changes its position inside the liquid. But when you tilt the body up to particular limit, then only it can oscillate. So that means the uniform oscillations of the body can be obtained when you tilt through a limited angle only. When there is a limited weight increase on the right side of the body, then only the proper oscillations of the body takes place. Okay, this condition we can take for deriving an equation for the metacentric height. So try to keep in mind this envelope which is the increase in weight of the body. And next here we can state one condition, movement due to increase in weight. So for getting the uniform oscillations, just now I told you, as we have analyzed, the tilting should be in a particular limiting condition. So not only that, we can state another condition which is the moment due to increased weight with respect to the neutral axis of the body should be equal to the moment of force of buoyancy due to its change in position with respect to change in position. So that means here for getting the uniform oscillations, for locating the metacenter, if you want to say that this body is oscillating and it is going to have a metacenter, means the moment of this W with respect to the neutral axis should be the moment of force of buoyancy with respect to the change of the center of buoyancy, that is the with respect to B point. So when these two are equal, then the uniform oscillations of the body takes place, then it can form a metacenter. That means with respect to a point it can easily oscillate. So that is the condition by which we can derive an equation for the metacentric height. So go for the representation here. So the distance between gm we need to find by the analysis this of this condition here. So now we go for the exact derivation part. So here I am assuming it is tilted to an angle of theta, and except that everything is same. Okay, and here we initially we need to find the moment of this particular weight. Okay, moment of this particular increase in weight only we need to find, moment due to the increased weight. So initially we have to know the weight of this increased part. So how will you find out means, for that I am considering one elemental area which is at a distance of x and which is of width dx. Okay, and for this particular strip, how can we write the weight? The weight of the strip can be written from the concept of, or from the definition of the specific weight, as weight of the strip is equal to specific weight into volume, we can write. Okay, now same from the definition of, or from the concept of the specific weight, we can write it as the specific weight of the strip as density into gravity. Okay, na? Density of that particular part into gravitational acceleration, we can write for the specific weight of the strip, into volume of the strip, how we can write it as area into length. Okay, so this particular area into the length of the body. So on back side of this projection we can observe the length. Here this is only front view, we cannot see the length, so that volume can be written as area into length. In the next step we go for extending or elaborating the equation, so which is rho gl as it is I have written, and in place of area what we can write, this elemental area we need to write. That elemental area can be written as, that is width dx into height of this element. So this height we need to find here. So in the next step we go for finding this height. So for finding this, consider a sector which is of length x and of height h. So I am considering the sector which is of length x, and the angle is theta only. Through how much angle you are going to tilt, with the tilt with the same angle it can be forming an envelope inside the liquid. That is only related to the increase in weight. So with that theta we need to find the height. So what is this height value? It is just like a chord length which is as small as it is, which is very small. So we can approximately consider it as a h only. So that chord length can be written as x into theta. Okay, so automatically here we try to modify the equation, rho g l dx into, in place of h we can write it as theta into x. Okay, so now this is the height. So now try to write as rho g l theta x dx. This is the weight of the only elemental strip here. Next we have to write the total area of the envelope, that is total weight of the envelope, that is total increased weight we need to write. So how can we write total increased weight? It can be an integration of this elemental area from this one to this one under the limits of neutral axis to the edge of the body. So we can write integration, whatever the formula we got, rho gl theta in x into dx. So after knowing this increased weight, we need to write the moment due to this increased weight. So the moment due to increased weight can be written as whatever the increased weight into, we can write it as the perpendicular distance. Here I am assuming the perpendicular distance as x only. Why? Because a smaller variation, smaller change in the weight is taking place. Okay, so I am assuming w, that is integration weight is this one, integral rho gl theta x dx. So write it as rho gl theta x dx into perpendicular distance becomes x only, I am assuming. Okay, so finally we can write it as rho g, that is integration of rho g l theta x square dx into l. So what do you mean by dx into l again? Dx is the width and l is the length of the body. So from the top view we can consider it is as a surface area. Okay, so dx into l is the surface area, not cross sectional area. So try to write surface area as a, rho g theta integration of x square dA. Surface area means we can consider it is as a plane area. So when you keenly observe this equation, integral x square dA, which is the second moment of area, second moment of plane area, which will be becoming moment of inertia of that particular uh, shape you are considering. So similarly we can write it as rho g theta I. Okay, so now again assume this one as equation 1. Next we have to go for finding the moment due to change in position of the center of buoyancy or force of buoyancy. Okay, moment due to change of center of buoyancy. So try to write what we can write, moment of this force of buoyancy with respect to change in its position. So that can be FB into, we can write it as BB1. So again, it can be FB can be written as weight of the body which is present inside, that we try write it later, and into we can write it as BB1. In place of BB1, it is also just like a sector. BM B1 is like a sector. So this BB1 can be written as theta into BM. So write it as BM into theta. So in the next step, we can write W, which is the weight of the body which is inside the liquid, in place of FB into BM into theta. So assume this equation as 2. So as per our condition, these two should be equal to get the uniform oscillations of the body with respect to the metacenter. So now make the two equations equal. So on both sides the theta is common, so try to cancel them, and remaining equation we can write it as Bm is equal to rho g I divided by W, which is the weight of the body present inside the liquid. So again we try to modify that. Rho g I divided by W of the body which is present inside the liquid can be written as again specific weight into volume of the body in the liquid. Okay, again rho g I by specific weight means we can write rho g into volume is represented by V, capital V. So rho g gets cancels, and the next remaining will be I by V. So Bm is equal to, we can write it as I by V. And finally what we need to know Gm. So Gm is equal to what we can write, Bm minus Bg. Bm minus Bg. Then it is equal to Bm, in place of Bm we can write I by V minus Bg. So that is only the equation for finding the metacentric height of the metacenter. So if you know the distance between the center of buoyancy and center of buoyancy and center of gravity, then we can find whatever the metacentric height it is going to take place whenever you tilt with any particular angle, by knowing the moment of inertia of that particular body and by volume of the body present inside the liquid minus the distance between center of buoyancy and the center of gravity. By knowing all these elements we can find out the metacentric height. So I hope you understand a simple explanation about a metacentric height, and the derivation of the equation of metacentric height. So if you still have any doubts, please feel free to give a comment to my video so that I'll try to clarify your doubts. And please subscribe to my channel and share my videos with your friends. uh, that's it, and once again thanks for watching my video. Thank you all.